Hi, all. Today we are going to discuss about engineering mathematics 2. We will discuss some of the very important previous year questions that were asked for engineering mathematics 2 in the university examination for BTech Food Technology. In this session, we will discuss only part A question. There will be another sessions discussing the remaining parts. This is first question. Two eigenvalues of the given matrix are 2 and 8. Then the third eigenvalue is. So here it is a 3 by 3 matrix. The given matrix is a 3 by 3 matrix and therefore there should be 3 eigenvalues. Need not be different, but there should be 3 eigenvalue for a 3 by 3 matrix. Now let it be lambda 1, lambda 2 and lambda 3. What is given? The first eigenvalue is 2. Second eigenvalue is 8. We are looking for the third eigenvalue. So for this type of problem, we will use some properties of eigenvalue. The first very important property of eigenvalue is sum of eigenvalues. Sum of eigenvalues is same as trace of the matrix. So what about trace of the matrix? Trace of the matrix is nothing but sum of the principal diagonal entries. This particular diagonal is known as the principal diagonal. The sum of the principal diagonal entries will be same as its that is actually known as trace. That will be same as sum of eigenvalue. Another one is product of eigenvalues. Product of eigenvalues is same as determinant of that matrix. We are familiar with the determinant. So these two are very important properties of eigenvalue. So since the first one is very simple, we have a sum of eigenvalue equal to trace. So what about the sum? It is lambda 1 plus lambda 2 plus lambda 3 is equal to the trace. What is our trace? 6 plus 3 plus 3, which is equal to 12. But we already know lambda 1 is 2 and lambda 2 is 8. What remains is to find the third eigenvalue. So 10 plus lambda 3 is equal to 12, and this implies the third eigenvalue lambda 3 is equal to 2. So these two properties, that is sum of eigenvalue equal to trace as well as product of eigenvalue is equal to determinant of A, are actually very important properties of eigenvalues. All should remember this. Now moving to the second question. A system of non-homogeneous equation is called consistent if and only if the rank of the coefficient matrix is equal to rank of dash. Is a fill in the blanks question. So first of all, you should know what is a non-homogeneous system of equation. Normally, this is denoted by A into x equal to B. For example, x1 plus 2x2 plus 3x3 equal to 4, 2x1 plus 3x2 plus 6x3 equal to 7, x1 plus 2x2 plus 7x3 equal to 8. So this is an example for a system of non-homogeneous linear equation in three variables x1, x2 and x3. Now why it is called non-homogeneous? Suppose if the right hand side, this is our RHS, the right hand side, if all this right hand side is equal to 0, then the system is called homogeneous. If all right hand side entries are 0, then the system is called homogeneous. If at least one of them is non-zero, here all these three are non-zero value, so it is a non-homogeneous system of equation. Now normally we will denote this system by Ax equal to B, where what is A actually? A is the coefficient matrix. What you have to write is the coefficient in order 1, 2, 1, 2, 3, 2, 3, 6, 7. Now x is actually the unknown values or unknown variable matrix x1, x2, x3, and the right hand side is actually denoted by b, that is 4, 7, 8. So this is our A, this is x, and this is b. Now this is actually called a non-homogeneous system of equation. There is a difference between a homogeneous as well as non-homogeneous. Now a system of equation is called consistent. What do you mean by consistent? If the system possesses at least one solution. If the system possesses at least one solution, that means at least one triplet x1, x2, x3 satisfying all these three equations, that is called a solution. If it possesses at least one solution, then we can say that it is consistent. If there is no solution at all, then it is inconsistent. The question is when it is consistent. The rule says that the rank of the coefficient matrix, that is actually the coefficient matrix is actually A, and the rank of the coefficient matrix can be denoted by R of A. This is equal to R of A B, known as the augmented matrix. Rank of A equal to rank of AB, where AB is known as the augmented matrix. It is actually quite simple to form this matrix. For this one, for the example, the augmented matrix is actually the matrix 1, 2, 3, 2, 3, 6, 1, 2, 7, and as the fourth column we will add the right hand side 4, 7, 8. So this matrix, this bigger matrix is called the augmented matrix. If rank of A is same as rank of AB, then it is a consistent solution. That is, there exists at least one solution. If this is equal to the number of unknowns, if this is equal to the number of unknowns, here in this case it is 3. If it is equal to n, then it is there is only unique solution. If the value is less than n, then there exists infinitely many solutions. That is actually the remaining part of that condition. This is infinite. Okay, in our case, is consistent. That means either unique solution or more than one solution, that is infinite solution. Then the answer is the rank of the coefficient matrix equal to rank of the augmented matrix. Okay. Here again we are discussing about rank of the matrix A. So first of all, what do you mean by rank of a matrix? There are different ways to define rank of a matrix. One of the important definition is it is the size of the matrix, largest matrix. It is the size of the largest submatrix with non-zero determinant. It is the size of the largest submatrix, which is with the non-zero determinant. That is actually a definition. So if we look at this particular matrix, what about the determinant of A? Let us start by checking the determinant. It is 2 into 0 minus 5 into 3. So what we are obtaining is minus 15, a non-zero values. That means the determinant of this particular matrix itself non-zero. So a matrix can be considered as a submatrix of that matrix itself. Every matrix is a submatrix of itself. So here the size of the largest submatrix with the non-zero determinant is actually 2 itself. So the determinant is the rank of this matrix is 2. That is one of the method. Another method is, or another definition is, it is the number of non-zero rows. It is the number of non-zero rows in its normal form or in its row reduced equivalent form. So either you have to convert the matrix to its normal form or you have to convert the matrix to its row reduced equivalent form. After converting the matrix to row reduced equivalent form or normal form, you have to count the number of non-zero rows and you can find the rank. Here A is actually the matrix 2, 5, 3, 0. Let us start by converting the first entry to 1. That is R1 changes to R1 by 2. So the equivalent matrix is, row equivalent matrix is 1, 5 by 2, 3, 0. Okay, now let us convert this particular entry to 0. What will happen? We have to change R2 changes to R2 minus 3R1. So what is equivalent matrix we will get? We will get, there is no change for the first row, 1, 5 by 2. This becomes 0. Here we will get 0 minus 15 by 2. That is equal to 1, 5 by 2, 0 minus 15 by 2. Okay, now let us convert this last final entry to 1. So R2 changes to R2 into minus 2 by 15. So the resulting matrix will be like this: 1, 5 by 2, 0, 1. Now, this is actually not the normal form, but is actually in the row reduced echelon form. You can see that the first leading entry here is 1. All the entries below that particular one is 0. And in the second row, first leading entry is 1. And there is no entry below that. So what about the number of non-zero rows? The first row containing at least one non-zero. So this is a non-zero row. This one also a non-zero row. So number of non-zero row is 2 here. So the rank is again 2. So either using the determinant method or using this reduction method, you can find the rank. Next one is actually from complex analysis. A point z equal to 2 at which a function f of z fails to be analytic is called. I will give an example for this. F of z equal to 1 by z minus 2. See, not that when z equal to 2, we have 1 by 0 form. So this function fails to be analytic at z equal to 2. Such points are called singular points. Such points are called a singular point, a point where the function fails to be analytic. Next is actually the concept of function. A function f of x is even function. And there are even and odd functions. Let us first define what is even function. An even function is defined as if a function f of x is even if f of minus x is f of x itself for all values of x. That means if you replace x by negative x, then the output remains same, then it is called a even function. I will give you an example. F of x equal to x square. If I take f of minus x, what I will get? Minus x whole square. And we know that minus x whole square is x square itself, which is nothing but f of x. So since x square eliminate that negative sign, we will get f of minus x equal to f of x. Then such functions are called even function. Another examples are cos x, modulus of x, x square, x raised to 4, etc. These are all called these are all examples for even function. Now what about odd function? Odd function is actually defined as if for a function f of minus x is minus f of x. f of minus x is minus f of x for all values of x, then it is called odd function. For example, if I take f of x equal to x, simply x itself, what will be f of minus x? F of minus x is minus x, which is nothing but minus f of x. Okay, so this f of x equal to x, we have f of minus x. That means when we change x to minus x, the output also changes its sign. It's called an odd function. Another examples are sin x, x, x cube, x raised to 5, etc. That means all odd powers, 2n plus 1. All even powers are actually examples for even function, and all odd powers of x are examples for odd function. So back to our question, a function f of x is an even function if this is our relation f of minus x equal to f of x. This is the answer, f of minus x equal to f of x. The Fourier series coefficient b1 in the expansion of x square. Here from the previous problem, x square is an example for an even function. X square is an example for an even function. And note that when you are finding the Fourier series, or in general the Fourier series is given by f of x equal to a naught by 2 plus sigma n from 1 to infinity an cos n pi x by L plus sigma n from 1 to infinity bn sin n pi x by L. This is actually a general form of Fourier series. So note that when you are finding the Fourier series of an even function, there will not be the bn part. There will be only the a naught part as well as an part. That is, for even function, f of x will be a naught by 2 plus sigma n from 1 to infinity an cos n pi x by L. This is for what type of function? For even function. And on the other hand, if it is an odd function, f of x should be a sine series that contains only sine terms, bn sine n pi x by L. This is for odd function. That is even function, for example, for sine, for cos x, for x square, for mod x, etc. We have a this type of, that is containing only a terms, a naught and an. For functions like sin x, x cube, x raised to 5, etc., it will be the sine series. Here the question is the Fourier coefficient b1 in the expansion of x square. But x square is even, and even since it is even, the Fourier coefficient, all Fourier coefficient bn should be equal to 0. That is, there is no coefficient of b in that series. So the answer is b1 is 0. Actually, all bn is 0. In particular, b1 also 0. The second order partial differential equation is hyperbolic. In the second order partial differential equation is hyperbolic. That means a second order partial differential equation, for example, dou square f by dou x square, let it be a plus b into dou square f by dou x dou y plus c into dou square f by dou y square plus etc. There will be other terms, that is like the first degree term, dou f by dou x, dou f by dou y, all will be there equal to 0. Such a function is called hyperbolic. When such a function is called hyperbolic, so what you are looking for, you have to look for b, c and a. That is, a is the coefficient of dou square f by dou x square, b is the coefficient of dou square f by dou x dou y, and c is the coefficient of dou square f by dou y square. If the value b square minus 4ac, if the value b square minus 4ac is greater than 0, then it is called a hyperbolic. If b square minus 4ac is greater than 0, then it is called a hyperbolic. If this value is less than 0, if the value is less than 0, then it is called elliptic. And if the value is equal to 0, then it is called a parabolic. Okay, so here the answer is the second order partial differential equation is hyperbolic if b square minus 4ac is greater than 0. A function f is called harmonic if dou square f by dou x square plus dou square f by dou y square equal to 0. Actually, the definition of harmonic function is a function f of z or a function f of xy is called harmonic if it satisfies dou square f by dou x square plus dou square f by dou y square, known as the Laplace equation. If it satisfies this equation, then it is a harmonic function. This is actually true. The function sin x cos hy plus I cos x sin hy is analytic. True or false? There are different methods to solve this, and one of the common method is you have to consider this as u plus iv form. So it is a complex function f of z equal to u plus iv. So what we will check, we will go for the CR equation. That is actually the general method, CR equation. What is CR equation? CR equation says that ux, that is derivative of u with respect to x, equal to vy, and uy equal to minus vx. So what about u here? U is sin x cos hy and v is cos x sin hy. Cos x sin hy. So what about ux? Ux is derivative of the function with respect to x. The derivative of sin x is cos x, and we have cos hy is a constant. Derivative of u with respect to y, sin x is a constant, and the derivative of cos hy is sin hy. There is no negative sign. Now vx is the derivative of cos x is minus sin x sin hy, and vy, the derivative of v with respect to y is cos x is a constant, and the derivative of sin hy is cos hy. Again, there is no negative sign. Now you can see that these two are equal, and this is actually the negative of one another. So the CR equation satisfies. And also note that the derivatives contains only trigonometric and hyperbolic trigonometric function. All hyperbolic and trigonometric functions are actually continuous. Since the CR equation satisfies as well as the derivatives are continuous, we can conclude that the function is analytic. It is true. Or in other method, this is actually the expansion of sin x plus iy. This is actually the expansion of sin x plus iy, and sin x plus iy is nothing but sin z. And we know that all trigonometric functions, sin z, cos z, etc. are actually analytic. Sin z and cos z are analytic. So we can conclude that this is actually true. Find the sum and product of the eigenvalues. Actually, already we discussed a similar type of question. What you have to sum of the eigenvalues, actually the trace of the matrix. We can easily find it, trace of the matrix, and product is nothing but you have to go for the determinant. I am not going to discuss it. It's actually easy. Determine value of an in the Fourier series expansion of f of x equal to x cube in minus pi. So in minus pi, x cube is actually an odd function. And for an odd function, there is no an term. An is always 0. So an equal to 0 is your answer. Does f of x equal to tan x possess a Fourier series expansion? So, to possess a Fourier series expansion, it should satisfy certain condition that is known as the Dirichlet condition. And the first condition is the function should be continuous. And we know that the function tan x is not continuous at many points. Tan x is actually, we know that it is sin x by cos x. So whenever cos x is 0, the function is not continuous at that point. So what you can conclude, the function is not continuous or not differentiable at that particular point. So there is no Fourier series expansion. Form a partial differential equation by eliminating the arbitrary constant a and b from z equal to ax square plus by square. So first of all, you have to count the number of arbitrary constants to be eliminated. What is that? It is 2. Now you have to count the number of variables, number of independent variables actually. Here we have 3 variables. X is a variable, y is a variable, and z is a variable. These 3 are actually variables. But one of them is the output variable. So z is actually the output variable or dependent variable. X and y are the independent variables. So what is the number of independent variable? It is 2. If you have the same number of arbitrary constant to be eliminated as the number of independent variable, then the resulting partial differential equation must be of order 1. That is the rule. If there is the same number of arbitrary constant to be eliminated as the number of independent variable, if there is 3 variable, you have to consider one as the dependent variable. So here it is 3 variable, x, y, z. Z is considering as the output variable. So x and y are the independent variable. So what we can conclude, the order of the partial differential equation is actually 1. That means you can use only the first order derivative. We can find dou z by dou x, that is actually p, small p, and small q, that is dou z by dou y. What is dou z by dou x? It is 2xa. And what is dou z by dou y? It is 2yb. So from that we can find a. A is nothing but p by 2x, and b is nothing but q by 2y. So substituting these two values in our equation, what we obtain? Z equal to p by 2x into x square plus q by 2y into y square. So we can cancel the terms, and taking this z 2 to the right side, 2z equal to xp plus yq. This is actually the required partial differential equation. 2z equal to xp plus yq. Classify the following partial differential equation. A partial differential equation is given, you have to classify it. That means you have to check it whether it is hyperbolic, parabolic, or elliptic. Here a, that is the coefficient of second order derivative with respect to x, is 1. This is 1. This is actually your b. 1 minus x is actually b. Minus 2, that is 1 minus x is b. C is actually the coefficient of second order derivative with respect to y, which is minus 2. So what is b square minus 4ac? B square minus 4ac. B square minus 4ac is 1 minus x whole square minus 4a is 1, 4 into 1 into minus 2. So it is 1 minus x whole square plus 8. Now the question is, for what value this will be negative and for what value this will be positive. For that we have to expand the term. This is actually x square minus 2x plus 1 plus 8. That is actually, this is sometimes denoted by s. For simplicity we can denote it by s. S is equal to x square minus 2x plus 1 plus 8. That is x square minus x square minus 2x plus 9. Now we are looking for the what value this will be equal to 0. So x square minus 2x plus 9 equal to, it's actually 9 plus 9 equal to plus 9 equal to 0. So we have x equal to minus b, that is using the quadratic solution formula, minus b, that is 2 plus or minus root of b square minus 4ac. B square minus 4ac is 4 minus 4 into 1 into 9, that is 36, divided by 2a, that is 2. So you will get some value. Let it be, I'm not going to find it, let it be some p and minus p. So you will get two values, p and q. So for these two values, for x equal to p and for x equal to q, for these two root values, we have s equal to 0. And when s equal to 0, the function will be parabolic. So when it is equal to 0, when it is equal to 0, we can conclude that it is hyperbolic. When the value is less than 0, when the s value is less than 0, it will be elliptic. And when the value, that is 1 minus x whole square plus 8, is greater than 0, it is a hyperbolic. Next one is the function f of z equal to z bar is nowhere differentiable, whether it is true or false. Nowhere differentiable means that is actually a complex function. Differentiable means we are considering whether it is analytic or not. So f of z equal to z bar is actually nothing but x minus iy. If z is x plus iy, now z bar is x minus iy. So u equal to x and v equal to minus y. What about ux? Ux is 1, uy is 0. What about vx? Vx is 0 and vy is minus 1. Now to satisfy the Dirichlet condition, ux must be equal to vy. Ux must be equal to vy, but ux is 1 and vy is minus 1. Therefore, the function is nowhere. There is no such points exist in which we have 1 equal to minus 1. So, nowhere it is analytic. So, nowhere it is differentiable. Consider the following partial differential equation. For this equation to be classified as parabolic, the value of b square must be, what will be the value of b square in order to classify it as a parabolic equation? So what is our a value? A is 3. B is actually given as b itself. C is actually minus 3. So to get its parabolic, we have b square minus 4ac should be equal to 0. B square, we don't know what is b square. So b square, it should be equal to 4ac, and 4 into what is a, 3 into minus 3, that is c. So it is minus 36. B square should be minus 36. 4 into 3 into minus 3. So we have b square should be minus 36, and that is not at all possible, because b square minus 4b square is a positive number. So we cannot find a b satisfying b square equal to minus 36. So one of the possibilities, b is equal to 6i, but that is not now we are only considering real values. Okay, moving to another set of question. A function f of x is said to be even function. A function f of x is said to be even function. We already know a function is even if f of minus x equal to minus f of x. That is the answer for first one. What about the second question? If lambda is the eigenvalue of a, then what is the lambda eigenvalue of a raised to minus 1? Now the rule is, if lambda is the eigenvalue of a, then lambda raised to n is an eigenvalue of a raised to n. So definitely, since lambda is an eigenvalue of A, lambda raised to minus 1 is an eigenvalue of A raised to minus 1. That is the answer for second question. A matrix is said to be diagonalizable if its eigenvectors are linearly independent. If a matrix possesses a linearly independent eigenvector, then only we can say that it is diagonalizable, linearly independent. Okay. Sum of eigenvalues of a matrix. We already discussed so many times. Sum of eigenvalues is actually trace of the matrix. That is the principal diagonal sum. If u of xy satisfy the Laplace equation uxx plus uyy, or in other words, dou square u by dou x square plus dou square u by dou y square, known as the Laplace equation, if it satisfies the Laplace equation, then it is called a harmonic function. It is called a harmonic function. Product of eigenvalues of this matrix. We know that product of eigenvalues is nothing but determinant. And since one of the row of this particular matrix is 0, one of the that means the third row is actually equal to 0. So here the determinant is 0. So product of eigenvalue is actually 0. Equivalent matrices. A matrix A is called equivalent. A matrix A is called equivalent to B if there exists an invertible matrix C such that A equal to C inverse BA, or in other words, or A equal to CB inverse CB C inverse. Two possibilities are there. Then A and B are called similar. Similar matrices are actually having the same characteristic equation. So the answer for this is either same characteristic or eigen characteristic equation, or having the same eigenvalues. Since the characteristic equation is same, then root of characteristic equation is actually the eigenvalue. So the eigenvalues are also same. So if two matrices are equivalent, then their characteristic equation are same as well as their eigenvalues are same. So the correct answer is eigenvalue. And characteristic equation also you can write, no problem. A partial differential equation of the form PP plus QQ equal to R is called the Lagrange partial differential equation. Lagrange PDE. This is called Lagrange PDE. PP plus QQ equal to R. A homogeneous system of equation is always consistent or inconsistent. So consistent means there exists a solution, at least one solution. Inconsistent means there is no solution. And what is a homogeneous system? Ax equal to 0, right hand side is 0. In such case, we called it is homogeneous equation. And note that if x equal to 0, if x itself equal to 0, then ax is always equal to 0. So x equal to 0 is always a solution of ax equal to 0. So a homogeneous system of equation is always, it is always consistent. That means there is at least one solution, that is x equal to 0, and is normally known as the trivial solution. The trivial solution. Define rank of a matrix. You already defined it. Either you can define it as the size of the largest submatrix with a non-zero determinant, or you can define it as the number of non-zero rows in its normal form or in its row reduced equivalent form. So that's the end of part A questions. We actually discussed all the part A questions from last 3 years, that is from 2021, 2022 as well as 2023. Now we will come up with another lecture in which we will discuss part B, part C and part D. Thank you.